All right, good afternoon, everyone. How is everyone doing? Busy having fun? Yeah. Okay, let's see. Where did we stop? We stopped here. Unit prefixes. Has everybody memorized this table? Has anybody memorized this table? Google is also in there somewhere. Okay, signal types. When we refer to signals in electrical engineering, signals can refer is we kind of use it as a synonym for like waveforms or functions, pretty much any kind of physical quantity like voltage or current. Okay, so signals can be used to refer to any kind of waveform or any kind of function. Two kinds of signals that we refer to or broad classification are analog and digital. Okay, analog and digital. So analog signals basically represent, if you represent an analog signal as a function of time, they have continuous values. So at any given point in time, it could have any value. All right. So technically, I would say infinite number of values, depending on where you measure the signal or at what point you measure the signal, you could have any value. Whereas digital signal are all about discrete values, and they only have two fixed values. Typically, digital systems used to be a 5-volt system. So it would be 0 and 5 volts, or now you have 0 and 3.3 volts. Digital systems, systems, whether they are analog or digital, they are still referring to voltage and current. The only thing is in digital systems, you only have two values, low and high. That low is 0 volts, high could be 3.3 or 5 volts. Most digital systems that we study or we learn as students, they're all 5 volts. Okay. All right. And so we have, there are two courses that you have to take regarding these systems. One is continuous time signals. The other one is discrete time signals. I'm assuming you have taken it or are taking it, right? 228 and what's the other one? 328, 228 and 328. You're done with both? You're taking 328 right now, yeah. Oh, 368 has some sort of like musical thingy that they have to do in there. It's a little bit more fun. Anyway, so that's what it is, right? So it's discrete values, and more often than not, we are simply working with two values, zeros and ones, low and high, binary number system. All right. Okay. Electrical systems can be made out of both analog as well as digital. And so we need to convert from one form to another. If you have analog systems, we need to convert to digital. We use ADCs or analog to digital converters. You go back and forth. We use DACs or DACs or digital to analog converters. So the way we would actually create a digital version of an analog signal would be to sample the signal, meaning take measurements of that signal at fixed intervals. So if we take measurements of the signal at fixed intervals, we'd end up with something like this. This process is known as sampling. And so the quality of the resulting digital signal depends on the number of samples we have. Obviously, the number, If the sampling rate is high, the more samples we collect, the more accurately we can recreate the original signal. So if you're trying to recreate the signal, we would take this and we would join all of these points together. Now you can see if you're trying to join these points, you would have something like this, not an exact replica of the signal. Does it make sense? It's not going to fit that curve automatically, right? This is just a representation, like a very basic representation of a digital signal. So you can see the more number of samples we collect, the more accurately we can represent or recreate our original signal, right? And so sampling rate is just one of the things when we refer to communications. And so that's analog versus digital. Then I just want to get into a few fundamentals. This is something that you're already aware of, but it always helps to have a refresher. So this is going to go by a little bit, quickly. Reference directions for both current and for voltage can use single subscript or can use double subscript. If it's double subscript for a current, it indicates the origin point and the exit point. All right. In simple terms, if you have a double subscript notation like IAB or IBA, the first subscript is the origin point. Or if you want to say we are in a lab, we take a meter and we are connecting it and measuring the current, then the first subscript is positive, the second one is negative. That's how we would connect the meter. If we are trying to measure IAB, we would connect the positive terminal or the positive end of the meter towards the positive, towards A, and the negative end towards B. IBA, be the opposite. It simply means current is flowing from A to B, or it's moving from B to A. First subscript is the point of origin. Second one is the destination. The IAB means it's flowing from A to B. IBA means it's flowing from B to A. And obviously, mathematically speaking, IAB is equal to minus IBA and vice versa. The minus sign simply indicates the current direction is flipped. That's all it means, doesn't mean anything else. All right. Same thing with voltage. If you have voltage VAB and you have voltage VBA, if you're trying to measure, means positive reference or positive terminal is connected to point A, negative is connected to B. VBA means the exact same thing. Okay. So VAB, meaning you're measuring voltage at A and your reference point is at B. And VBA, same thing, measurement at B, reference point at A. That's the double subscript notation. Later on in this course, when we get to transistors, and let's see, and in the lab 346, when we look at the BJT experiments, there will be a triple subscript notation, ICBO, ICEO. It's basically collector to base current with the emitter open and with the base open. And so there it's not referring to points, it simply means something else. All right. But if it's a double subscript notation, this is something you should keep in mind. All right, notations. You're going to be working with DC as well as AC signals. Point where I said diode circuits and especially transistor BJT circuits. We will measure the voltages across the terminals of the device. And when we measure the voltages, we'll have both DC as well as AC. Okay, so it's important to note notification. The total signal in a circuit is comprised of both DC as well as AC. Okay, DC as well as AC. To note DC, we use uppercase. And to note AC, we use lowercase. Uppercase or capital letters, lowercase or small letters. uppercase and lowercase signals. So our total signal is usually comprised of a DC plus an AC voltage. And the way we represent it is the quantity itself is in lowercase, and then the subscript T is uppercase. And that indicates that we are referring to both, or the quantity is referring to both DC as well as AC values. Okay. All right, let's take a pause. Let me know if you have any questions before I just do an example. Okay. All right, so just using the example of the transistor, there are three terminals of a transistor: collector, base, emitter. One of the most common voltages we measure is VBE, which is the voltage at the base and the emitter. So if I was to write the voltage, the base, and the emitter, lowercase v, uppercase B and E. VBE is voltage measured at the base with my reference at the emitter. So VBE. And VBE, total VBE would be comprised of the DC value of VBE. So it'd be VBE plus VBE. Okay. So the AC notation for V would be lowercase v. And if you're measuring just AC, both the base and the emitter, the B and E would also be listed as lowercase. So VBE. And that would be the total signal. So VBE, first right here, is the total signal. As an example, we could say V of t, function of time, is 3 plus 5 sine omega t. Mathematically, just random example. It's a random example, right? DC and AC do not mix, but mathematically, when we write it, we can write it like this. A DC constant, whether it's 3, 4, 5, 10, 15, doesn't really matter what the value is. And then a description, mathematical description of the function. Obviously, we cannot combine it. So it'd be just, this represents DC and this represents AC. Make sense to everyone? Okay, a bit more refresher again. All right. What's the difference between these and these? They're all power supplies, right? Yeah, there's lots of show of hands. Yeah, go ahead. Absolutely. And I heard someone else say the same thing on this side too, right? So circle ones are independent sources. And the diamond ones are dependent sources. Independent sources simply means that the sources do not depend on anything else to supply its rated quantity. Hence, that makes them independent. Everything that we use in everyday life, they're all independent sources, right? Our benchtop power supplies that are on the lab benches behind you, the batteries inside your smart devices, the power supplies inside our consumer electronic devices, they're all independent sources. It does not depend on any external input to supply its rated voltage. It's inherent. Whereas the diamond-shaped ones are indicating dependent sources. So it depends on some other quantity in some other part of the circuit to supply its rated quantity. Okay. The reason I'm bringing this up is because there are there are other models that we'll use for our transistors even for our op amps, where we use dependencies or dependent sources within those models. Because the transistor has 3 terminals, so we can split it up into 2 parts. One is the input side, one is the output side. Same thing with an op amp or any kind of amplifier. And the output side will have a dependent source that depends on either the input voltage or the input current. And so transistor model specifically will have dependent sources inside it. All right. So yeah, that's the dependencies. An example, a very simplistic example, could be a voltage divider circuit. Okay, if it's a voltage divider circuit, voltage divider circuit is, let's say you're applying plus 10 volts, and this is, I don't know, 3, and 4 ohms. Okay, 3, and 4 ohms. To make it around, okay, it's 10, right? So you'd have 3 volts here, 3 volts here, and 4 volts here. If you take the output from here, you would have 4 volts. That 4 volts may be being supplied to some other part of the circuit. Now, if that 10 volts changes to 20, what happens to this output? Changes to 20 volts. Anyone? Doubles, right? Elementary school math. 8 volts. So that voltage across that 4 ohm resistor is being supplied to some other part of the circuit. It is supplying a voltage, so it's a source technically, but it depends on the voltage that is applied in a different part of the circuit. If that voltage changes from 10 to 20, the output voltage changes from 4 to 8. Just a very simplistic example. But again, as I said, we will use these models typically in BJT and FET models. Okay, BJT, FET, and op-amp models. Just as a generic question, as an EE, what makes a source a voltage source or a current source? Have you ever seen a current source, by the way? Anyone? Nobody has seen one? Seriously? You've been in labs, in the EE labs? All right, glad I'm doing this slide. All right, so what makes it a current source? Nothing except the mode of operation. The benchtop supplies that we see in front of us, or at least behind you on the lab benches, they are both a voltage source and a current source. If you run a source in constant voltage mode, it's a voltage source. If you run it in constant current mode, it's a current source. That's it. There's no other difference. So benchtop supplies, I mean the power supply units, the PSUs that we have in all the labs, they are voltage as well as current sources. So next time you're in the lab, if you're in my lab, I'll point it out. But next time you're in any lab and you turn on the DC power supply, you look in at the top of the screen, somewhere there will be a CV or a CC. Constant current mode is not something we use. Very rarely do we use that. Most experiments will run in CV mode. So those power supply units will show you CV or CC. So CV mode, so this is the mode of operation. CV mode will mean we are running is as a voltage source. And this would mean we run it as a current source. That's all it means. Okay. Taking it one step further, the explanation for this is constant voltage, constant current. What it means is the power supply unit will change the current, but keep the voltage constant. Let's say you have a power supply rated for 10 volts. Right? It should supply 10 volts at its output terminals, no matter what is connected. What happens if you connect a 100 ohm resistor? What is the current I? 0.1 amps, right? 10 volts applied to 100 ohms gives you 0.1 amp. What if you connect a 10 ohm resistor? What is the current? 1 amp, right? What is the supply doing? The supply is set in constant voltage mode, so it is supplying 10 volts, does not change the voltage at the output, but it changes the current that is being supplied based on the requirement of the load. If you connect a 1 ohm source, 1 ohm resistor, the I should now be 10 amps. So it's changing the current value based on the requirement of the load. So it's running in constant voltage mode. That's what makes it a voltage source. Same thing for a current. A current source will supply its rated current. I'll leave that as an exercise for students. But you have a current source. Let's say it's 1 amp. Let's say it's 10 amps. And make it simple. If you connect a 100 ohm resistor, actually not 100 ohm, let's just do 1 ohm resistor. The voltage is 10 volts. If you connect a 10 ohm resistor, voltage is now 100 volts. If it's a 100 ohm resistor, it's now. So that's why we put current limits and voltage limits. We are running in any other mode. If we run it in constant voltage mode, we put a current limit on it. We don't want it obviously going all the way to 10 amps. We put otherwise the circuit would blow out. And if it's a constant current mode, we put a voltage limit on it. So it's not gonna be able to supply 1,000 anyway. Most power supplies are limited to 25 or 30 volts. Still, we have to protect our circuit. Okay. Going on a slight tangent. What if this is 0 ohms? What is I? Infinity, right? It's infinity. I is infinity. If voltage was not 10 volts, instead it was, let's say, 0.1 volts, and my R is 0, what is my I? Still infinity. Hence, short circuits are very bad for power supplies. Right? A few years ago, we had the exploding phone. Anyone remember that? Samsung Galaxy Note 7. In the pursuit of making the phones thinner, engineers in their design factory or battery design factory, the batteries inside these phones are made up of individual cells. The cells are connected in series or in parallel, depending on how they design it. So the walls between individual cells were made very thin, which resulted in shorting out the positive and the negative terminal. Shorting out the terminal means your resistance is now 0. There's a short circuit. And the resistance is 0, doesn't matter how small the battery is, it's a short circuit, current is infinite. What happens when there's a closed loop? Electrical energy is supplied. If it's a very small battery and you have a short circuit, it's going to supply that battery, it's going to supply the energy until it's exhausted. Even a small battery still has tons of capacity. So if you take a small coin cell and you go on the beach, don't do it, but I'm just saying, if you want to do it, then go on a beach surrounded by sand and you have a small coin cell, like an old one, and you short the terminals. If it's some capacity left, it's going to expend that energy. That energy is dissipated as heat, so it gets hot. The hotter it gets, sorry, the more energy that is released, the hotter it gets. With a small energy, like a really old battery, might have some energy, it's dissipated, it's gone, it's done. It's a brand new battery, even if it's a small cell phone, that is a large amount of energy that is stored in there. So the short circuit in the battery released all of that energy all at once. It's releasing the energy, it's still not run out. Battery still has capacity. So it's releasing and releasing and releasing. One point gets really, 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 really hot, and then boom. That's what happens. And so when you're working in the lab, any lab, the most important thing you can do right before you begin is to set the current limit. Always set the current limit. Otherwise, you're going to end up blowing out the power supply and your circuit. Your circuit is fine, less than $10, doesn't really matter. But if you blow up the power supply, there's a few $1,000s. So we always want to set the current limit for power supplies. Doesn't matter whether you're a student, you're a working professional engineer, this is something you should keep in mind. All right, any questions? Yes. Fixed current through a short. The question being asked is, can we run fixed current through a short circuit? What do y'all think? Not if it's the power supply. If it's anything else, like it's just a point in a circuit, then yes. So the answer to your question is yes and no. So if it's any other circuit, you simply have 2 points in a circuit, you want to send current through it, then yes, you can run a current through a short circuit as long as it's part of a larger circuit. But if it's your power supply and you just short other terminals, then that's a no. We don't want to do that. All right. Let's see. So what approach do we take in solving our problems and our models? Okay. There are some steps that are outlined in the book, and there are some steps that I add on to. So the absolute first thing you want to do is you read the problem statement. Okay. We want to read our problem statement. You want to determine what it is that the problem is asking of us. Read, comprehend the problem statement. What is it asking? What do we need to find, right? Then the next step is to extract as much information as we can from the given problem. So the statement itself will have a lot of things. Now, when I say extract information from the given information could be in words, it could be in the circuit diagram, it could be in a graph that accompanies the circuit diagram. Okay, you need to observe, note everything, and record everything and extract as much information as you can. As an example, you could have a circuit. That circuit has, let's say, a few resistors and a power supply. The resistor values could be noted on the circuit diagram itself or in the circuit diagram itself, or it could be noted somewhere else in the problem statement. You could just say all resistors are 1 kilo ohm in words, not listed on the circuit diagram at all. Or it could be listed on the circuit diagram. Then the power supply might not be given to you. It might just state here, 5 volts, 0.1 amp. If you read just the problem statement and move on, you're missing information. There is some information that is given here, right? So extract information from the circuit diagram. And then lastly, you could also have a graph that describes a quantity. It's V or I, voltage, current, power, energy, doesn't really matter what kind of quantity it is. But pay attention. Time could be in seconds or milliseconds or microseconds. Here, this could be in volts or millivolts. Current could be in milliamps, microamps, or nanoamps. That is also information. If you miss noticing this from the graph, your answer is going to be incorrect, even if the process and everything is correct. Okay. Anyone ever see Robin Williams' live on Broadway? He had a comedy special that came out a few years ago called Live on Broadway. And he points out, it's really funny, by the way, not suitable for work or here, but do it at your own time. Really funny. At one point, he's talking about, he's making a joke about how there was this Mars lander. So engineers were working this Mars lander. Mars lander went up. It's trying to land on the Mars, on the surface of Mars, and it crashed. So now they're trying to do an analysis of why it crashed. Well, apparently it turns out that they made the calculations in like inches and they programmed it in meters. This is a real thing that happened. He made it. He was not making a joke of it. He was just stating facts. And it seems very funny, right? Because it was like a collaboration between scientists at JPL, the Jet Propulsion Labs in LA here in California, and I think NASA offices in, I can't remember, Colorado or somewhere. Can't remember where. I have to read up that history. So when the handover occurs from one office to the next, there was someone who was in charge, or there's a team which is in charge of converting those in measurements. And someone will drop, or maybe a whole team dropped the ball. They performed the maths in different units or different unit prefixes, and they programmed it in different units, resulting multi-million-dollar spacecraft crash lands on the surface of a planet, which is a real life thing that happened. So as engineers in training, it's very important that you pay attention to details. You know how in job descriptions, they say, if you're looking for candidates,